Can you write in terms of current nature or to write? If I want to write this answer in terms of current, it is Vt ln of Id by Is. In the first classes of diodes, we know how to write Vd to Id, Id to Vd. If I write Id to Vd, it's exponential. If I write Vd to Id, it's a logarithmic. So we created a logarithmic function now. Using diodes, we done it. So it is minus Vt ln of Id by Is. Id is the diode current, forward current. Is is the reverse saturation current. This diode current is same as your input current coming from the Vi. So you can write this answer as Id, we can write it as IIN divided by Is. You can write like this. IIN divided by Is. But according to the board, your IIN is nothing but VIN minus 0 divided by R. So what is this current here is? It's an input voltage minus 0 by R. So if I substitute that one in the original equation, it's minus Vd ln of. Your IIN can be written as VIN divided by R into Is. So can you see that your output is proportional to ln of your input? This I proved in the class. So your output is proportional to logarithmic function of your input. This makes me to tell you it will behave like a log amplifier in electronics. What do you mean by log amplifier means? If the DC, if you use suppose 10 volts, DC you are giving to the circuit, the 10 volts will become close to 0.1 volts. That means you are compressing the data in electronics. So in communication field, whenever you want to send a lot of package of data, in terms of DC you're sending suppose information, 10 volts means a lot of information. I want to compress it in the channel, then this type of circuits are better. It will just compress the values. You have given 10 volts, but answer is coming close to 0.1 volts. Okay, that is called as compression circuits or companders we call in communication electronics. But this idea is better only in your lab when you do, because the diodes are eligible. But in real estate designs, integrated circuits, diodes are not there with us. Only BJTs are MOSFETs. Then how to make the same function with BJT class? Suppose if I want to design in integrated manner, how to design is, you have to take our same circuit. This is minus, plus, and just your transistor you take like this. This is output. This is ground. It's telling that you can use in place of diode, a BJT you can use it. It will work like a log system, it's telling. In place of using diode, we can use BJTs also. So how means simple logic. If this is 0, this current is IIN. This current will become your IC current. This is your diode. This will have a voltage of VBE, base emitter voltage. So this transistor will work in active region now in the class. So if it works in active region, what is the output here? Seeing the board is 0 minus this voltage will be the output. So the output will become simply minus of VBE in this case. Minus of VBE will be the answer for it. 0 minus VBE, so answer will be minus VBE. Minus VBE is nothing but diode voltage drop. So you can write simply minus VD ln of IC divided by IS. In place of diode current, we write as IC current here. So the formula is same. It is IIN divided by IS. So you get the same expression, minus Vt ln of VIN by IS into R. So if you use diodes or use BJTs, they do the same thing. In exam point of view, anything is okay. This is used for discrete electronics, that is used for integrated electronics. These log systems are used for integrated circuits. Integrated design. It is integrated design, log system technique, special technique for integrated designs. Because in integrated ICs, we don't have diodes, we have BJTs or MOSFETs. But don't use MOSFET there, okay? MOSFET is somewhat different compared to BJTs. BJT have the diode properties like this, but MOSFET does not have the diode properties. MOSFET have parabola type of characteristics, so that will behave in some other manner. If we keep MOSFET, let's see MOSFET also how it is going to behave. This is the log system analysis. Suppose I'll write a note here. Note. If MOSFET is kept as a feedback. If anybody asks you, then what happens? If MOSFET is kept as a feedback, then the circuit will behave as a square root amplifier is telling. It will behave like a square root amplifier. So you will get just V naught proportional to under root of input. You will get like this. So in exam point of view, by chance, if I give MOSFET as a feedback, don't tell that is a log amplifier. It will become full. Because it is a parabola type of answer. ID is equal to some Kn into Vhs minus Vt whole square you are doing. That square will become, other side will become root. So it will work like a root function actually. Okay? No need of drawing the diagram again. Just logic you keep in mind. In exams, the logic he may ask you. So square root amplifiers will get. Such type of mathematics we can provide by MOSFETs. Okay, diodes can provide logarithmic mathematics. BJT also logarithmic, but the systems will do square root functions because they are parabola functions. So this is about my log analysis. Topic number 3 is completed here. I am entering to topic number 4 now. Topic number 4. Anti-log amplifier, how to make with opposite amplifier technique. If there is a log system, we can make it as anti-logs in electronics. If there is a log, we can make anti-logs. A very important topic it is, most of the times. In exams, they'll ask you log system calculations. So be perfect. This is the way how I'm calculating the log analysis. So anti-log is opposite to the log system. You have to prepare now. Okay? Log and anti-logs are opposite to each other. So I'm entering to the 4th topic now in the concept. 4th topic I'm entering now. So examiner can ask you with respect to BJT or with respect to diode, both have the same analysis. So don't get tension when you see BJT is there. Okay? Both will perform in the same manner. One person will will use diodes when you want to use. You can use in the labs. In breadboards we can use it. But when you go to IC design part, BJTs we have to use it. Okay. So let us cover the fourth topic. Let us complete the fourth one. Anti-lock amplifier. Anti-lock amplifier. Anti-lock amplifiers. If I want to design an anti-lock, I am going to change the devices part now. Minus plus, plus is ground. Here output. The only thing what I am doing is resistor which is in series I kept in shunt. Opposite I am doing. The diode is kept in shunt position. We kept in series position. So this is called opposite mechanism. Okay. Here also compulsory the DC only has to go into the picture. So this is the way how I am interchanging the subject. Previously diode is in shunt. Resistor is in series. Now resistor became the shunt and diode became the series. So how it is going to complete now? If there is a resistor, 100% it's a closed loop, so 0. This current will be your diode current, forward current, and it will have some voltage VD. This current will be IR current. So now you can do the relation. So first ID current we'll find out. ID is equal to IS into e power VD by VT. I have written the class. And diode current equation I have represented. But VD and VIN both are same. These two are same because VN minus 0 is VD. So ID we can write it as IS e power VIN divided by VD. So your VD and VD became same in the problem. So VD will become VI. But what is ID here is, it will become IR. This IS into e power VIN by VD. What is IR here is 0 minus V0 by R is equal to IS e power VIN divided by VD. So what is your relation I am getting is V0 is equal to minus IS into R e power VIN divided by VD. So this is your relation. You can see now output is proportional to e power input. We are getting this type of link in the class. Output is proportional to this one. Just 1 minute. You complete up to there. So suppose if I design the same op amp, if I want to design with BJT suppose. In integrated electronics, we have to design with BJTs now. Here you keep same resistor only R. Up to here there is no problem for you. Just now the thinking is this diode should be in forward you want. Whenever you want forward, which type of transistors we have to select here, that is important. Here we have to select some transistor. What type of transistor is better here? So that I can send the current in forward direction like this. If you want to send the current in forward direction, PNP is better here. So PNP you have to take because the current has to go in forward direction. Your diode is here, base emitter junction diode. This is the replacement I have done. So it will be 0. This you will take it as some IC current. This current will become your IR current. Same process again. Okay. Your IC current, we can just write it as IS into e power VBE divided by VD. Your VBE is this voltage. VBE became VIN. Same analysis you can do it. Okay. Same procedure. So IC can be written as IR here. IR is equal to IS into e power VIN divided by VT. IR is nothing but 0 minus V0 by R is equal to IS into e power VIN divided by VT. So V0 is minus IS into R e power VIN divided by VT. So this completes the package of 4 applications. Okay, 4 applications are completed. One is address we completed. Sir, can we take any other configurations of BJT? Divya, thus that depends on your diode movement. Here I am explaining diode forward. If diode is reverse, suppose given in the exam, then you have to take this NPN you have to take. According to the movement of the diode you have to take. So just 1 minute. The power is off here. That's why. Just for 1 minute, voice will not come. Wait for 1 minute. Wait for 1 minute. Now only fluctuation came. So maybe voice will not come for 1 minute. Just wait for 1 minute. Yeah, it's coming. You can see here, note, who will take diode in this direction, then you have to take here, NPN transistor is better, because your diode movement will be like this. So this is the replacement if the diode movement is opposite given in the exams. Sometimes we cannot use MOSFETs. I already told you MOSFET is somewhat different application called as square root amplifiers in the previous topics we can use. MOSFET we can use only for that particular case. Here for log systems, anti-log systems, whenever you want, MOSFET kabhi bhi use nahi karna because that is a parabola. Log system is a word comes only for diodes and BJTs. Okay? Then how can you think like that? Yeah, power fluctuation if it is there for 30 seconds, you may not get voice, so don't worry. Kabhi fluctuations are there, so don't worry about it. So the only thing is when the diode, if you keep like this, you have to keep NPN transistor in your model. Nothing more than that. Just moment wise you have to change the position of the transistor. Sometimes NPN, sometimes PNP we have to use it. now I think the voice is audible for you. Just now only again, power came. Please one time recheck. If the voice is clear, we'll go for the next one, fifth topic I'll explain. Fifth and sixth topic are parallel topics. So I'll explain both topics at a time. 5 and 6 will be completed parallelly. These are the two interesting applications we use in communication electronics. So we'll take like an example and I'll explain you the fifth and sixth topics. Okay, done. Great. So fifth and sixth we are doing at a time now. The fifth topic we have is analog multiplier. So for what purpose I use analog multipliers means it's a very popular application in communication called modulator we call this as modulator. So what is the meaning of a modulator means? Suppose if I design an IC like this is not an op amp, it's an IC. In this IC we have several op amps. Okay? It's a modulator IC we call. Only in the exam you'll see only one cross mark like this. This whenever you see a cross mark, it's a multiplier we call this IC name. This is output here. For multiplier you'll have two inputs like this. One is Vx and one is Vy. And you'll have some scaling factor. We call this as a DC factor. We call this as VR. We call this as scaling factor. Scaling factor we call, which is a DC required for the IC design. So this is the way you'll see a separate module in your applications. This is called a modulator IC we call. It is not a op amp actual. Inside we have some log systems and the log systems we kept. So inside what is there I don't want. Examiner will give you a diagram like this and they'll ask you what is the output response for that. So students should know how to write the answer for a multiplier IC. The answer for this is simple form like this. Your output will be equal to Vx into Vy. These are your two inputs. By whatever you are telling a scaling factor which is a DC voltage that will come down. So this is the formula for a multiplier circuit in electronics. So Vx into Vy divided by Vr. Examiner will give Vx, Vy and Vr some values. You just find out this answer, Vx into Vy by Vr. I don't want to prove it all these things. It will divert my syllabus. Okay? Just only formula result is important here. So what is the reason to have modulator? That I give you a small idea about communication electronics. Suppose if I take this as a signal like this, it's a having more wavelength and this is having less wavelength. So you can see two different things I have taken. This is called low frequency, this is called high frequency. High frequency we call it as carrier signal we call in communications. Carrier signal, and this is called as modulating signal we call. Modulating signal. Like this we have two signals with us. One is modulating signal and one more we have is carrier signal. Carrier signal is not information source. Modulating signal is our information. Modulating means maybe my voice signal is a low frequency source. It is called information. This signal alone cannot go in transmission because low frequency signals, if you keep there, okay, at the receiver side, the antenna size will become very, very high. If you want to reduce the antenna size, a high frequency carrier you have to send, then the antenna size practically it is better to keep in meters. Otherwise it will go in kilometers. So the antenna size reduction also we can do with this technique. So that's why whatever the voice signal you have, which is a low frequency signal, you can transmitting like that. To make the trouble to overcome, that's called antenna size in the receiver. We take high frequency carrier to superimpose with low frequency. When these two are superimposed called multiplication, we call it as modulation. So these two has to modulate with this IC. Therefore we got Vx, Vy. But not only that, this IC is giving some error here, but scaling factor is also coming here. Okay, some scaling factor is coming here. So Vx into Vy divided by Vr. So Vx is information source. Vx is information voltage it is. And Vy is a carrier signal which we don't want. Carrier which is unwanted. At the receiver side, I don't want this unwanted. Only I want this one, I don't want this one. Not only this one, I don't want this also. Vr. Only this answer has to come at the receiver side. Then what this person has done, see here. He has used a technique called analog divider. At the receiver side, they'll keep a divider circuit. We call this as demodulator we call. This is called demodulator. So what do you mean by demodulator here is, suppose this is your VIN having a resistor R. I kept a op amp, basic op amp. This is your output. This is R. Again, that multiplier I kept as a feedback here. So you can see the demodulator diagram. Multiplier is easy, straightforward answer, but demodulator has some structure here. Using op amp and using again multiplier as a feedback. This feedback is a multiplier IC I kept for your basic op amp in the receiver side. Finally, the output, whatever we are achieving, that should be Vx we want because that is an information source. Remaining things has to cancel. That's why demodulator what it will do. Yeah, thus this scaling factor is nothing but a DC voltage here, which will be given from external source. Okay, it's a scaling factor is nothing but a DC source. Then only the circuits are working inside. Otherwise, without scaling factor, they're not working actual. The log systems inside. So that's why a scaling factor is very important. But PR. So now the point is, this input is from where it is coming is from your output it is coming. So just this output, whatever you are seeing, is your input now in the class. This is multiplier, that is receiver, transmitter, receiver. Transmitter I designed this one, receiver I designed this one. So the transmitter output will become the input. So what is this input we are expecting is, it is Vx into Vy by Vr is your input. I'm expecting that is your input. So this input when it go here, this is a closed loop, so zero virtual ground. This current will take it as I. The same current will go I here. This is your multiplier output is Va. What is multiplier output here is Vy into V0 divided by Vr. So here what happened is, one input is V0, one input is Vi. Scaling factor is Vr. So what is the relation between these two voltages? If you want, you just write the KCL here. KCL at V minus. Okay, this you take it as I1, this you take it as I2. These two currents should be same now. So I1 should be equal to I2. So VIN minus 0 by R should be equal to 0 minus VA by R. So you got a relation between VA to VIN in the class. Yeah, Samresh, it's just like a biasing of the circuit, correct? There must be some biasing voltage there. So VA, we are getting it as minus of VIN according to KCL. So VA becomes minus VN in the concept. Okay, but what is VA here is Vy into V naught divided by Vr, that is becoming minus Vn here. So you want an output to input relation now. So just reverse this formula. If you reverse this formula, we'll get the structure of your output. Your output can be written as simply minus Vr into Vin divided by Vy. So can you see the divider here? What do you mean by divider means? This is your carrier signal. Again, you are giving same carrier. This is your same carrier at the transmitter. Same thing you are given. Carrier is dividing with your input. Okay? Your input by carrier is coming. That is called divider. So what is the answer will come with this formula is V0 is equal to minus Vr into what is Vin here is Vx into Vy divided by Vr divided by Vy. So this is the actual simplification you can see output how you are getting. So Vy carrier will cancel, which is unwanted. Your scaling factor will cancel. So output will become minus Vx. So finally the answer came as output is equal to minus Vx. But sir, Vx चाहिए minus Vx is not required. Then what I'll do is I'll just connect to this. One phase shifter in the design. I'll connect a phase shifter application. Then automatically your output will become Vx. So finally Vx is nothing but my information source. This is my information. So this is the story how they are going to use analog multiplier and analog dividers. This application is a very okay. Most of the time they will not ask you this question. By chance there are some competitive exams where they are asking these questions. So you should have a clarity like this. Okay, the circuit we are using for demodulators. So the way of doing problem is very easy. Consider the steps how I am doing. Just you find out this multiplier output. You just have a relation between these two and just invert it, you will get the answer. This formula you have to practice. This formula minus Vr into Vn divided by Vy. So this completes my package. 5th and 6th topic are completed. 5 and 6 at a time. Just by interlink I have been covered the class. So last 2 more topics are there. One is phase shifter, what I can say. Fourth integrator and differentiator. If you can cover these 2 topics, mathematical operations will be completed in the class. Mathematical operations will be covered. So one is modulator and one is demodulator circuits. Multiplier answer is very easy. Vx into Vy divided by Vr. So let us see how to design an integrator concept now. The next step is integrator concept. These are very important topics. Integrator is very important, which are widely used in most of the times in my circuit analysis. Let's see the most important idea, integrator. Differentiator is not that much important in our application, but integrator is most important. So let us concentrate well about integrator design. So 6th topics are completed, 7 and 8, 2 more topics. So keep the heading, 7th one. 7th topic I'm explaining. 7th one. Integrator, keep the heading. Integrator. If I want to design an integrator concept, what I'll do is, I take op amp, minus plus is grounded. We have a resistance R. Here what I'm doing is, I'm keeping capacitor as a feedback. Previously we kept diodes and BJTs, now capacitor I'm giving as a feedback. The capacitor we kept as a feedback. Yeah, the whole configuration. Shall we? Second circuit is called dividers. First circuit is multiplier. So in multiplier we don't have any op amp externally, but in dividers we have a multiplier is also there and op amp is also there. That is a divider technique. So this is our integrated design. Capacitor I have taken. If you take capacitor, you can close it by 0 so that you can charge the current. This is I you take. This current will be IC because we have to apply AC here. So let us use the small letters here. We are using AC analysis here. Your II, IC current. Capacitor will charge. AC wise you can charge it. So the current if it goes there to the C value, you can expect what is output will come is here VC voltage will provide. So 0 minus V0 will become VC. So output will become simply minus VC. So I think this is the result we are getting. So what I understood is whatever the feedback component you are giving, the drop is your answer with a negative sign. Okay. Previously you kept a diode, so minus VD. You kept a BJT, we got minus VB, so here minus VC. But what is capacitor voltage formula here is, it is 1 by C integral of IC into dt. The relation between voltage to current is an integration. So output will be equal to minus 1 by C. Your IC current and IA current are same. So you can write II into dt. But what is IA here? It is VIN by R is your IA current. So V0 you can take it as minus 1 by C integral of VIN divided by R into dt. So the output can be represented as minus 1 by RC integral of VIN into dt. So this is actually the integrator concept. So your output is proportional to integration of input. It's inverting integrators because inverting integrators we generally use most of the times. So we have some negative sign. This RC will become the time constant. Okay? Where RC is called time constant. RC we are calling it as a time constant. So now I want to learn some extra things about integrator. Let us understand. After getting this knowledge up to the relation how to find the integrator, let us see the transfer function of an integrator is what. Let us find out the transfer function for this. I'm finding a transfer function for this. transfer function for an integrator, which will tell about the behavior of its response in frequency plot. So let us see, again I'm drawing the diagram. So can I take this as some RF here, and we'll take this as some R1. So if you see clearly this circuit, it's just looking like an inverting amplifier in the class. It's just looking like an inverting amplifier. So V0 if you want, it is minus RF by R1 into VIN. So this is your output I have written. Minus RF by R1 into VIN. So output can be written as simply minus 1 by j omega c divided by your R1 becomes R into VIN. So if you want a trans function here, V0 by VIN, we can write as minus 1 by j omega c into R. Like this we are getting V0 by VIN in the class. If you want in magnitude, this answer trans function in magnitude. This is your trans function, output by input. If you want in magnitude, your V0 by VIN in magnitude, it will be 1 by omega c R. So this is the answer we are expecting. Root over omega square r square c square, root will be cancelled. So it will become 1 by omega c R. So this is called an integrator trans function. I proved it. Now the point is how to write a frequency plot for an integrator. If you want an integrator frequency plot, you can see how it will come. This is your omega, and this is your gain. Gain versus omega, you can see the plot, integrator plot. If omega is 0 in the class, if omega is 0 means you started from 0 frequency, I think V0 by VIN is becoming infinite. So it is having infinite here. So the gain is becoming infinite. Okay, the gain is infinite. But when you are going for practical systems, the gain cannot go to infinite. Maybe the gain can go to AD. If it's a practical amplifier, the gain cannot go to infinite. It can get to open loop gain called AD. This much gain you can get at omega equal to 0. Okay, because infinite we cannot write. Ideally it is infinite, but practically the voltage will get saturated, correct? So it will have open loop gain actually, AD. And when omega comes to infinite, what happens? When omega comes to infinite, V0 by VN will become 0. So if you are going towards infinite, I think your integrator response will go like this. Your integrator response is going in this manner. At omega equal to infinite, it will become 0. So this is called integrator waveform. Integrator is working in this manner. That line have a slope of, this integrator line have a slope of minus 1 by RC. Just it is integrating the value in the slope with a negative slope like that. Okay. So this is about the story. Can you feel that whenever you have at omega is lower frequencies, you are telling that the gain is infinite or the gain is AD. That means the high gains we are getting at lower frequencies. Because of this, we have some trouble with integrators. At low frequencies, it will become more unstable. At high frequencies, it will become more stable. Because whenever you have more gain, the system will become more unstable. So integrators will become unstable at lower frequencies, but higher frequencies they will become stable. So to avoid this problem, we have to do some rectification called practical integrators. This is a theoretical integrator. Okay, the circuits cannot work in the labs. Let's see the point, and we'll finish this content. So please complete it up to here. So there must be some modification we have to do for an integrated circuit now. Because lower frequencies, the gain is becoming very high, so the integrator will become more unstable. So how to make it stable at lower frequencies is important for an integrator. If I want suppose 0 decibels, if I want to find out this answer, let us write this graph in a clear way. We'll write separately this graph. It just complete up to here. Neatly I'll draw the diagram in the next slide. Up to there, please complete it. I want to convey some more information about this concept. So today I'm planning to stop at a differentiator. I'll stop it. So you are going to have relief of time. I'm expecting 4:10 or 4:15. The class will be completed today. I'll stop it today. I'm not interested to teach after 4:15. Tomorrow I'll start from there. So you can have a relief up to 5 o'clock. The SAR will start at 5. You'll get a 45 minutes break today. 5 o'clock SAR will start. Tomorrow we'll see. If I want an extra time, we'll see tomorrow. Okay? Today we'll finish up to differentiator. Tomorrow class we'll complete morning class. When I come from 8:30, we'll start the first precision circuits. After that, active filters. These two topics I'll cover first. Then I'll go to the nonlinear applications. Okay? So today I think it's enough for me to complete today's class. By 4:15 I'll stop the class. By completing this issue. Only thing is a differentiator I will explain after this content. So let's see. The frequency plot, if you see clearly, the frequency plot. Okay? This is omega versus gain. Suppose if the gain is in decibels we have taken. This will become 0 decibels then. For 0 decibels, there will be some frequency called FT, unity gain bandwidth frequency. Because 0 decibels are called unity gains. And your integrated response is coming like this. It will touch FT. 0 decibel is also called as unity gain we call. In magnitude, we call it as unity gain. So now you can solve what is FT formula in integrated circuits. This you can take it as AD. Okay? And the slope of this line is minus 1 by RC. So if you want to solve what is FT in the class, your previous trans function, if you see, V0 by VIN, we got in magnitude as, how much you got? 1 by omega CR we got. 1 by omega CR. 1 by omega CR. So this answer, whatever you're seeing here, this answer will make it as, here we'll take it as F otherwise, in terms of F will solve. So here unity gain you want, so 1 I'll take here, magnitude wise, is equal to 1 by omega T you have to keep. When you get 1, here omega T, R into C. What is FT here? Is 1 by 2 pi into RC. So actually this is the formula of FT in the design. 1 by 2 pi R into C. Whatever the R you have taken, whatever the C you have taken, with that you can find out the gain bandwidth product in the integrated circuits. Okay? So now the point is how to calculate bandwidth for your integrator. Up to now FT I calculated. So and at lower frequencies I can write here one point. At low frequencies, integrator will be unstable because of high gain. So how to solve this problem? Just we'll rectify the problem. We call it as practical integrator will apply. Just we'll design a practical integrator in this concept. Yeah, come Mundal. You may get a new subject, don't worry. When they start offline, okay? If suppose they are starting offline, they'll keep it. Otherwise, they'll send you a new live video again, okay? Don't worry about that. Because we cannot predict what will happen in future because they will prepare all these timetables, all these things. So what they have, their mind, I don't know, okay? Whatever they say, according to that, we'll follow it. Future thinking, don't do it, okay? We'll get headache because of future predictions, we cannot do anything. Let's see what happens. Saturday, definitely, you'll get the information, what will happen. Now, presently, networks is going on, concentrate on networks. Yeah, Ditya's unstable meaning is it's going to be to saturation. Okay, unstable meaning saturation mein ja rahe. Humko, we want to work in linear, not in non-linear region. But you are going to saturation. It's not the meaning that the device will damage. Non-linear region mein ja rahe. So, practical integrator should not go to non-linear. Then how I design is, we'll take here minus this plus. We have here one R and here one capacitor C. And what I'm doing here is I'm keeping one parallel resistor Rx to the capacitor and I'm taking the output. You can see a small modification I've done in my practical integrator. Okay, just I kept one resistor parallel to the capacitor because at low frequencies we know that capacitor will become open circuit. At low frequencies is opening. When it opens, the op-amp is not working on the closed loop, it's going to open loop system, so it's becoming unstable. So it has to be in closed loop. Okay, that is required. So that's why what I've done is I kept a cap above the C. If you keep a cap like this, now this total content will become your RF in the class. This will become your R1 so that the trans function will change naturally. How much the trans function is coming? Let us see. So first, what is RF simplification? You can do it. It is Rx parallel to 1 by j omega C. So it is Rx into 1 by j omega C divided by Rx plus 1 by j omega C. You can write like this. Rx into 1 by j omega C divided by Rx plus 1 by j omega C. So this can be represented as Rx by 1 plus j omega C into Rx. You can write like this. J omega C is cancelled. So Rx by 1 plus j omega C Rx. This is RF value. So what is the gain formula here? AF, otherwise trans function we can say. So the trans function here is output by input is equal to minus RF by R1, which is equal to minus Rx by 1 plus j omega C Rx divided by R1. So like this you can make a trans function. Okay? You can make a trans function. So output by input, you can write it as minus Rx by R1 divided by 1 plus j omega C into Rx. So you can write in magnitude the trans function, how much it is. Magnitude wise, it is Rx by R divided by root over 1 plus omega square Rx square C square. So this is the way how you are finding the trans function. Okay? Now can you see the practical integrator, what happens? With this trans function, if omega is equal to 0, if I keep here omega equal to 0, this total answer is 1. So Rx by R we are getting the gain. So we are not going for high gain, we are going for low gain. So high gain systems, we are making low gain systems by this technique. So that at low frequencies also the integrator circuit will be stable. At high frequencies it is already stable, but low frequencies also it will be stable. That is the meaning what you want to tell. So can you find out the bandwidth? In the exams they'll ask you, what is the bandwidth for this? So according to the board you can see, here only I got it, you can see. This is your gain now we got like this. This is Rx by R we are getting. At low frequencies we are getting Rx by R, which is a low gain. At that time, if we want to solve FH, how much? That is your higher cutoff frequency will be how much for that. Then you can solve it very easily with this technique. That is 1 by root 2 technique you can apply. So Rx by R by root 2 you applied. Your gain has to fall by root 2 times. Rx by R divided by root over 1 plus omega H square into Rx square C square. So this Rx square, Rx will be cancelled. This root we can cancel. So omega H square, Rx square, C square. You can take it as 1. So Fh is equal to 1 by 2 pi Rx into C. So this is your answer for 3 dB frequency. So this is called bandwidth. Okay. So in exams most of the times you require this information, how to calculate 3 dB frequency and how to calculate FT. These two formulas are important. So that's why I am taking care about these formulas. FT means 1 by 2 pi RC actually. FH means 1 by 2 pi these two values. Rx into C will give the bandwidth. The components will change. Okay. So where is the integrator I can use now in the class? Integrator can work from here to here now. From this point to this point will work as an integrator. So practically if you want to put integrator, so always use your frequency should be less than FH, should be less than FT, more than this one. In this range we can use as a good integrator. Good practical integrators we can say. So this is the way how we are using an integrator circuits. Practical integrators if you want to use, this is the range we are using as integrators. So below this how can you use the region means, why can't you use this like a low pass action? So below FH, these integrators will behave like low pass, above they'll behave like integrators. So this is the story actually. Below FH we are using like low pass, above FH we are using like integrators. So that's why indirectly we call integrators can also be called low pass. Okay, low pass responses, integrators means. So the last topic is how to give a relation for differentiator. We don't want to do all the stories for differentiator. Straightforward we can write the answers now. Okay. The last point is differentiators. So let us complete differentiator and we'll stop the class today. Tomorrow we'll continue from precision rectifiers and active synthesis tomorrow morning class. Tomorrow morning, we shall here both sides root functions I cancel here. Both sides root function I cancel. Yeah, and thus whenever you find the bandwidth, you have to take this as gain by root 2 times you have to take. That is called 3 dB. We call 1 by root 2 times you have to take and cancel it. Okay. So this is an important information about integrator concept. Just give me 5 minutes to complete the final issue for today class. I just round up the class today with this idea. So let us complete the last topic called differentiator is the final touch. Okay, tomorrow there are some beautiful topics, morning class. 8:30 will start the tomorrow class. Okay, timing is 8:30. Okay, tomorrow timing will be tomorrow. There's a practical way of explaining the concept. Okay, anybody want exactly the bandwidth? We should not take it the same value. We have to take 1 by root 2 and we have to solve it. Here graph में नहीं दिखा रहा हूँ वो point. उधर दिखा रहा हूँ. This is an approximate graph. Okay, this is an approximate graph. So last topic. The last topic is 8.1. Differentiator. It is not that much important to study, but a basic idea should be there. How to design a differentiator. Differentiator, how to design. This minus, plus. First you keep capacitor, and next you keep resistor. Oppositely you do it. You will get the differentiator from integrator concept. This is 0 here. Virtual ground. This current will take it as IC. This current will take it as IR. This is VC. So you can write from the board what is IC relation is. C into dVC by dt. So the relation between a charging current to a voltage is a differentiation. Okay. So VIN and VC are same here. So IC can be written as C into dVIN divided by dt. You can write like this. VC, VIN both are same. VC, VIN both are same. But IC and IR are same. So IR is equal to C into dVN by dt. You can write it. IC is equal to this relation. So IR is equal to C into dVN by dt. But it is 0 minus V0 by R is equal to C into dVN by dt. So output is coming as minus RC dVN by dt. So you can see the link how I provided. Output to input is a differentiation relation. So this is not a much important topic. Maximum in the competitive exams, they try to ask you integrators, they never ask you differentiator. But a basic idea you must have. This is the basic idea. This is more than enough for studying differentiators. So we got a relation here. V0 is proportional to dVN by dt. It's just an opposite of integrators. So this is more than enough for this topic today. So here, we'll try to end up the concept up to here. Tomorrow class 9th and 10th topic will cover morning. Okay. After that we'll proceed with the final topics for non-linear applications. Maybe tomorrow workbook I'll not start. First I'll complete the theory part for you. After completion of that, if time permits, we'll do the workbook after that. Because now the questions are 60% of the workbook questions we have completed off. Only hardly some 40% is there. That 40% we'll do at the end of the concept of completion of the total theory part. Okay. First we'll finish the total theory analysis. So tomorrow 2 modules we have to cover. Okay. One is the subpart is remaining and remaining is non-linear applications. Then we can do the workbook.